and that's going to correspond to, because that's on the far end, but we're looking at the convolution going this way, in a sense. So we have, so just roll with me here.
Hello, and thank you for watching my video. This is called Quadratic Polynomial Number Theorem, and it is a generalization of Euler's pentagonal number theorem, and we'll see what that means for known results, and we'll look at some new things too. And this is a submission to 3 Blue, 1 Brown's Summer of Math Exposition 1, SOME1. Thanks, Grant. This guy and gang for inviting me. All right, let's leave identities for the moment and focus on the second part of this episode, which is recurrences for partitions and for the sum of sigma divisors function and others it leads to. But essentially, recurrences...
Let me just state it. It all comes down to our indicator sequence. As you recall, for regular partitions, the sequence is 1, and then it's all -1 or a +1, depending on whether it's a pentagonal numbers. And so we get
0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
This is basically playing on symmetry convolution thing that we have going on, and how there's a structure in here. Both ends talk to each other, even to the infinite. There's a sense in which this is true. And what it boils down to is that we can take whatever partition of whatever n we want, and let's say it's P of 11, and that's going to correspond to, because that's on the far end, but we're looking at the convolution going this way, in a sense. So we have, so just roll with me here. P11, we'll assign it to that, and then since we're looking at what's coming from this end, we're going to be counting down. So P of 11, and then minus P of 10, minus P of 9, and then 8, 7 are zeros, and then we have a plus P of 6, 5, 4, 3, 2, 1, 0. All right, we never make it this far, and we have all zeros out to there. And obviously, if we had chosen P12, then we would be moving to here, and then we would start a negative cycle again with P0, which would be 1 by definition. So if we back substitute our values,
1, 1, 2, 3, 5, 7, 11, 15, 22, 30, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
We have 56.
Minus 42.
Minus 30. Plus P of 6, 0, 1, 2, 3, 4, 5, 6, that's plus 11. Plus P of 4, 0, 1, 2, 3, 4, which is 5.
Giving us a total of
56 minus 1 is 14, negative 16, plus 11 is negative 5 plus 5.
Equals 0. And what Euler proved and what this proves is that this will always equal 0 for all n, and we end up with the recurrence
P of n minus P of n minus 1 minus P of n minus 2 plus p of n minus 5 plus p of n minus 7,
etc. And we go to a limit until the generalized pentagonal number that you have here exceeds n, and we end up with a negative number, and part p of n less than 0 equals 0 by definition. So people will often express this sum in terms of going to infinity, which is a little disingenuous because there's always a finite limit, which is n minus f of k, such that n minus f of k is less than 0. So this recurrence can be written, if we put all of this to the other side of an equal sign, we can have a recurrence for Pn equals the sum from k equals 1. And I'm not going to say infinity, I'm going to say, so by pushing everything off here onto the right hand side, we can get this recurrence for p of n equals the sum from k equals 1 to, and I'm not going to say infinity, I'm going to say k such that f of k or f of negative k is less than or equal to n. That way either our regular pentagonal numbers or our negative side generalized pentagonal numbers, the quadratic has all positive values except for the 0 at f equals 0. So once either side exceeds n, then we're getting a negative, and a p of n equals 0. So expressing the limit this way, we actually have two components because we're doing a single k on the positive side. So for our first component here, that corresponds to the f of positive k, and this corresponds to the f of negative k. So we have this factor, negative 1 times, and when it's on the right hand side, these will be positive, so negative 1 and k equals 1, k plus 1, so that we get a positive here, of p of n minus f of k. And let's do this because we have a split here, plus p of n minus f of negative k. Alright, so that keeps our signs straight in pairs, and these are our pairs 1, 2, 5, 7, 12, 15, etc. And so this recurrence is a very famous recurrence from Euler, and one way of seeing this is let's just start with our partitions in an index, an index starting with k equals 0. And we have 1,
2, 3, 5, 7, 11, 15, 22, 30, 42.
and let's just let that be our top matter, k equals 0, 1.
2, 3, 4, 5, 6, 7, 8, 9, 10.
We can look at the entire sequence p to the n for all of p to n's, and then do these for the whole sequence. In other words, at k equals 1, I am adding, in other words, at k equals 1, or at k equals 1, we are adding n minus f of 1, which is 1, so p of n minus 1, and then that's n minus 2 there, obviously. So, but if we just fixated on this and looked at what happens to this as n goes from 1 on up, we're going to have a sequence placed at 1, at the 1th position, that is essentially a copy of this. So
1, 1, 2, 3, 5, 7, 11, 15, 22, 30.
and then we're going to be adding n minus 2, so that means we'll advance to the 2 here. Again, it's just another copy.
1, 1, 1, 2, 3, 5, 7, 11, 15, 22.
And then when we move to k equals 2, then we're going to have 5 and 7 with a negative sign.
Negative 1, negative 1, negative 2, negative 3, negative 5, negative 7.
And in our 7th position, we'll have a negative
1, negative 1, negative 2, negative 3.
And the next one would be 12, so we're not there. So we're done. And we can add these up. 1, 2, 3.
5, 7, 11, 18, 16, 15, 26, 23, 22, 37, 32, 30, 52, 45, 42.
And we recover our sequence exactly, only offset by our 0 is not here anymore. So that's the recurrence. We've recovered Pn from manipulating these sequences of Pn. Another interpretation of what we're doing here would be that we are starting with a copy in the first position and it is multiplied by 1. Well, what if we took that sort of sensibility and said, well, how about in the second position we take a copy and we multiply it by 2? Why do we do this? Because we are exploring, and that's it. But when we do that, we end up with, well, let's just do it here. 2, 2, 4, 6,
10, 14, 22, 30, 44.
and then, so this one here would be multiplied by 5, so we'd have negative 5, negative 5.
Negative 10, negative 15, negative 25, and negative 35, and by 7, negative 7, negative 7, negative 14, and
Giving us 1, 1, 3, 4, 7. Not 33. It can't be 33. Derp. This is 21. 18. All right. So, but well, what are these numbers? They're funny. They're not strictly increasing. They go up and down. Presumably, we were a number theorist or a savvy mathematician, then we might very well recognize what these numbers are. They are sigma of n, which is the sum of divisors function. So for the number 1, there's one divisor. For the number 2, there are two divisors, 1 and 2. Their sum is 3. So 1 and 2. And for 3, we have 1 and 3, which sum to 4. For 5, we have, for 4, we have 1, 2, and 4, which sum to 7. For 7, we just have, for 5, gotta go by our index here, 5.
we have 1 and 5, that's a prime number, 6. 6 is a perfect number, 12 is a perfect number, but 6 we have 1, 2, 3, 4, 6, and 12, and 6. I'm doing 12. 1, 2, 3, and 6 are divisors of 6, and their sum is 12. Similarly, 1 and 7 sum to 8. And for 8 we have 1, 2, 4, and 8, that's 12, 14, 15. And for 9 we have 1, 3, 9, summing to 13. And for 10 we have 1, 2, 5, and 10, summing to 18. So
That's by making that switch where we multiply in the generalized pentagonal number, we get a sequence that is equivalent to sigma n, the sum of divisors. Similar to what we had before, very, very extremely similar. Sigma n equals,
the sum from k equals 1 to k such that f of plus minus k is less than or equal to n of negative 1 to the k plus 1.
and exactly the same thing we had before, except we're going to put in this factor in front. So we have f of k times p of n minus f of k
Plus f of negative k times partitions of n minus f of negative k.
So it looks, it is exactly the same thing. All we're doing is inserting this factor in front here. And And so we have this recurrence, which Euler also proved. And there are two more. Okay, so we have partitions in terms of partitions and sigma n in terms of partitions. Okay, we looked at that one, we changed the rules and got that one. Well, let's look at these two together, change the rules for this one, and see what we get. And the way we're going to change the rules is to take this form, go back to this with just a coefficient of 1 in front of all of these, but instead of the partition numbers, let's see what happens if we substitute in sigma itself. So we're going to look at basic sum of sigma of n minus 1
plus sigma of n minus 2 minus sigma of n minus 5 minus sigma of n minus 7 plus sigma of n minus 12.
dot dot dot. What does that give us? Well, we can do a similar thing we did before, where each row is the sequence of sigma n minus 1, and then the sequence sigma n minus 2, etc. So let's start with an index and the basic sequence of sigma. So we have k equals n sigma k. For sigma of 0, of course, with partitions of 0 is 1 by definition. For sigma k, there's something funny coming up, but we need to discover it organically. So let's just put in this bracket symbol for now, for sigma of k, or sigma of 0, I should say. Sigma 1 of 1 is 1.
So 3, 4, 7, 6, 12, 8, 15, 13, 18,
12 and 28. Those are the sums of divisors for these k values. Okay, so first up, sigma n minus 1. Well, that is going to have the impact of shifting this sequence forward this way here. So let me put this symbol here for 0. And then 1, 3, 4, 7. -7, -6, and then for 12 we are eventually going to have a plus our 0 symbol. Well, I'm going to start with just a sum without the brackets, so that we can take a look at what might be happening here. So let's just look at what we do know without having to consider these, and that's 4,
7, 12, 20 minus 5 is 15, 23 minus 10 is 13, and 28, 22, 18, 31 minus 19 is 12.
and we got these things here. So, and the reason I avoided that, well, take a look. What do we got here? We've got 4, 7, 12, 15, 13, 18, 12. So that's telling us that 13, 15, 13, 15, 12, 8, 15, 13, that's telling us that this wants to be 8. But this is 18 minus 3 is 15. So what get 8, it must be minus 7. This is 11, it should be 6, so this is going to be negative 5. And we'll get our 6. And then this 1, 4, 3, this should be 3, so this here has to be 2. We get our 3 here. We're going to need a 1 here, so this has to be 1. And 28, this has to be 12 to give us our 28. Similar to what we did before, we have used sigma values at n minus generalized pentagonal numbers. to express sigma in terms of sigma. So we have a sigma
n in terms of
sigma k less than or equal, no, just less than n. It's p k less than n. Sigma n in terms of partitions p of k less than n. And the left-hand side of this then is going to be sigma n, obviously. So we have sigma n
equals the sum from k equals 1 to k such that f of plus or minus k is less than n of negative 1 to k plus 1 times sigma n minus f of k plus sigma of n minus f of negative k.
Now that we've done that, well, let's talk about this little trick. As you can notice, and again, this is all Euler found all of this, that what we ended up inserting here is the actual number, which is whenever n is equal to a generalized pentagonal number, then we are going to substitute n into our funny brackets that we used for 0. So that's the little trick, is that when it is when n is a generalized pentagonal number, we take sigma of 0 to be n. Okay, and here's the fourth one, which is also probably Euler, but the source is a little confusing. Some people say Lagrange or Laplace, I can't remember. McMahon detailed it. Ramanujan and G.H. Hardy mention it in their famous circle method paper. And there's a paper from Erdos where he proves it, like with a single sentence using a double sum form. It was probably Euler, because it's not that far from these other ones, and he discovered all of those. But anyway, it goes like this. And that would be n times the partitions of n. This is I'm just going to call it a convolution identity. And identity between p and sigma. So npn, n times the number of partitions of n, is equal to the sum from k equals 1 to n. So we've got solid limits now. Sigma of k times p of n minus k. And that's it. There's no plus minus. There's no funny business with the limits. There's no funny business with any trick. Straight up. And not too hard to see that the switching the arguments gives you the same thing. Really straight up, simple and super nice. So let's look at the numbers on that. Okay, so we can put p of k of n minus k here, n minus 6, this will be 0, so we can go backwards. 1,
2, 3, 5, 7, 11.
All right, let's multiply these together, at least these positive ones, because we don't have a k equals 0 in our index. So 7, 15, 12, 14, 6, and 12. N is 6, so 6 times partitions of 6, which is 0, 1, 2, 3, 4, 5, 6. 6 times 11 equals
22, 34, 48, 54.
66. All right, there's our answer. So sigma of n minus n, here we do get a sigma 0 here. if we think of it doing the same trick, 0 is among that quadratic of the generalized pentagonal numbers, and the idea is to substitute in k or n when it's on a 0, so 0 times 11 is 0, plus all of that equals 66. So those were 4 recurrence identities, all due to Euler, probably. Maybe this one was somebody else, but it was early days. And since then, there's been all manner of recurrences found, I mean, in different forms, based on different types of numbers and things like that. But more so than the recurrences are all the identities, especially identities, partition identities using modular criteria or other restrictions, or restrictions to prime powers or other number theoretic functions like the totient function and the tau function, aka the number of divisors, not the sum of divisors, but the number of divisors. It's a very interesting playground. I am grateful to the Summer of Math Exposition project and the idea of it, that here's a place where we can informally share mathematical teachings and information and research in a less formal environment without a bunch of poppycocking and hogwashing. And so I appreciate the opportunity to show what I've got going on, and that's it. Thank you very much for watching my video.